Okay, so we've talked about continuity. First off, we have functions which are continuous at a single coordinate x equals a. And then if a function is continuous across its whole domain for every single value of x where that function is defined, we just call that function a continuous function. Continuity is the property where we can substitute in when we are calculating limits. So this video is talking about, we have some basic functions which are continuous, but what other functions are continuous too, which is to say which other functions have limits which are easy to compute. So there's two major theorems, and again, these are taken directly out of your textbook. I'm going to assume that f of x and g of x are both real valued functions, and they are continuous at some coordinate that I'm calling a. And I'm going to use c here to denote some real number, just a fixed constant. And I have 5 new formulas of different functions which will also be continuous at the point x equals a. The first formula is that f of x plus g of x is continuous. The second is that f of x minus g of x is continuous. The third is that the constant c times f of x is continuous. The function f of x times g of x is continuous. And finally, the function f of x divided by g of x is continuous. And again, this theorem is just for continuity at the point x equals a. But if you assume that f and g are both just continuous functions at every point in their domains, these rules will still work for every point in the domain of your functions. So the only thing I've got to watch out for is, as usual, the division by 0 case. And what this means is I can break up my limits across addition, subtraction. I can factor constants out. I can treat limits separately when I'm multiplying 2 different functions, and I can treat limits separately when I'm dividing 2 functions. These are all things that I've mentioned about limits previously, but the idea carries on to talking about when functions are continuous or discontinuous. The second theorem that I want to talk about is about the composition of 2 different functions. So again, let's assume that f of x and g of x are 2 different functions. I only need to know that g of x is continuous at x equals a, and f of x is continuous at the point x equals g of a, right? So I need to be a little bit careful with this one. I'm composing the 2 functions, right? F of g of x. So whatever my output from the function g is going to be the input for my function f. So if I put in x equals a, g of x gives me g of a, and f of x is going to, we're putting in g of a as for the input for my f function. My output is going to be f of g of a. Got to say that right. So I can nest continuous functions inside of each other, and the result will still be continuous. So this lets me combine the formulas of different functions and still get something that's continuous at the very end of it. So for example, let's take the function x squared. I'm going to write this in parentheses just to facilitate my composition here. The function y equals x squared is a polynomial, so it is continuous. And that means that at any point x equals a, the limit as x approaches a of the function y equals x squared is just going to give me a squared as my limit. So I like to imagine that as I can draw this function just by tracing with my mouse, and I never have to let go. There's no gaps, there's no jumps, there's no holes, there's no asymptotes. I'm going to compose this function with something else. So I'm going to put in cosine of x. Now I have the function cosine of x, which is then squared. So the cosine function by itself is continuous. Again, I can draw it without letting go on my mouse. There's no holes, there's no jumps, there's no asymptotes. But I can continue to put more complicated things inside this formula. My function might move around a bit, but here I have cosine of x plus 3 squared. This is still a continuous function. If I like, I can say this is cosine of 5x plus 3, which is then squared. All of these manipulations are just nesting continuous functions inside of each other, and we can see off of the graph that I still have a continuous function that I'm working with. If I like, I can take a radical in here. The square root function is continuous, so I can say cosine of the square root of x. But you notice that half my function vanished. What happened? All of this is contingent on the functions being defined. So the square root function is not continuous for negative values of x. It's not even defined there. And you need the function defined as a prerequisite for it to be continuous. So notice that when I did that, my composed function, so in the very most inside I have a square root function. In the middle step, I have take the cosine and add 3, and the final step, square what you get. This is a nice continuous function, but only for positive values of x. Again, I am limited, I am constrained here, I'll say, by the domain of the function that is the very most nesting here. So at any step in this process, if I have a function that's undefined for a certain input, I don't get continuity there. So in this example, I don't get continuity at negative values of x. To return to an example I've used before, let's have cosine be the outermost function. So I'm just looking at cosine of x. Let me zoom in a bit. And I'm going to put a different function inside of the cosine. I'm going to put in 1 divided by x. Now, the graph of 1 divided by x looks like this in blue. Turn off the cosine there. So this is continuous, except at the coordinate x equals 0. Coming in from the left, I'm going to positive infinity, it looks like. Coming in from the, from the left, I go to negative infinity. From the right, I go to positive infinity. Neither of those are real numbers. So this function is discontinuous at x equals 0. And that is carried into the function cosine of 1 on x. This is something that we've seen before, where the y values keep oscillating between 0 and, between -1 and 1, and they will never settle down to have a limit. So this cosine of 1 over x function does not have a limit at x equals 0. The reason for that is because the 1 divided by x function also does not have a limit when x approaches 0.